The second session this morning, and the first speaker is Professor Matt from École Polytechnique.
Thank you. So from Lady X at École Polytechnique. So what I will present today is some idea on what I will try to pass on to you is this idea of convective non-normality, and you will see I will try to maybe propose another name for that, a better name, and so I will discuss the interplay between lift-up and convective non-normality on two examples, if I have time. The recirculation bubble and the wake, and this is work done by Olivier Marquet and Philippe Milligat that were a PhD and that are PhD student at ONERA, and it's a collaborative work with Denis Sip. So the type of flow I want to describe today is what I call an open flow, what has been called an open flow. So this is one example. So this is a flow in a duct, and here you have a smooth backward facing step. So you have a recirculation bubble, and this flow, and you want to describe the stability of that flow, and to understand the dynamics of this type of flow. So what is specific for this type of flow, open flow, is that you have the flow will exist in a finite domain. You have some inlet condition. You have a mean transport of perturbation, for example. And this flow will also evolve spatially. So this is not a parallel flow. And what you should do, if you want to study the linear dynamics of that, is that you will linearize the flow around this base state, the first step to understand the dynamics of the flow. And then you will solve for eigenmode. And in the next of the talk, I will call that global eigenmode, and you will see why. It's just a name to recognize the theory compared to another theory that will be the local theory that will look at the local dynamics of perturbation. But this is just simply an eigenmode, so you have to solve an eigenmode for this mode, and in that case, the streamwise direction will be an eigen direction for that. And now you may imagine that there is two types of behavior that you may describe with this type of tool. The first type of behavior is when you have an oscillator, so when this flow will bifurcate. So this is simply due, you will have that if there is any eigenmode that will have a positive growth rate. So this is very easy to describe, but we also know that this type of flow may behave as a noise amplifier. There may be a very strong and efficient way to amplify small perturbation that you will put on the system. And the description of this noise amplifier is well known in this community. It will be due to the non-normal behavior, so the non-normality of the linearized Navier-Stokes equation for that flow. And this non-normal behavior, you may say, okay, this is due to the fact that all the eigenmodes here are not at right angle. They are making very small angle between each other. So, so this is an idea that we propose also with Carlo Cossu here in the room. And what I will try to illustrate this idea of the non-normality of this global mode. So first, maybe for some of you, if we just want to have a very simple idea on non-normality, one very useful concept is to imagine that you have eigenmode. And now you may define if you have a scalar product. So this is the way you will measure energy in the system. So this is your favorite way of measuring things in the system. And with this favorite way of measuring things, you may define the adjoint global mode. And an adjoint global mode is just an eigenmode that will be orthogonal to all the other direct global mode, except the one with the same index. And then this adjoint global mode is a very convenient way in the system, because since now you have a scalar product, and you know a base that is orthogonal to the base of the direct eigenmode, you may project the dynamics. If you want to project the dynamic of the system on one particular eigenmode, then you just have to do the scalar product with the adjoint eigenmode for the same mode. For example, if you take an initial value problem, so U0 is the initial value that you start with. If you want to compute the linear dynamics of the flow, you have to project on each single eigenmode, and you will project on one eigenmode, so you may compute the coefficient in front of this eigenmode by doing the scalar product of the initial condition with the adjoint, and the coefficient will be scaled by the scalar product of the direct and the adjoint mode. So this is just a convenient way to project the dynamics, but now when the flow is highly non-normal, what will happen? If the flow is normal, the direct and adjoint global mode are the same mode. but when the flow is not normal, the direct and adjunct global mode makes an angle that is very close to 90 degrees. So they may be nearly orthogonal to each other. This means that the coefficient here may get very large if this is very close to 0. And this is the idea. So this will give rise to this transient growth process. If you start with a small initial condition, this small initial condition may expand on very large coefficient on these two modes. And if one mode is damped faster than the other, you will have the dynamics, the UT that will grow, the energy of UT that will grow and then decay. So this is the physics behind this transient growth. Another useful idea about this non-normality things is that now let's imagine that you have the linearized operator that corresponds to this eigenmode, and you perturb this linearized operator. And when you do that, you will move around the eigenvalue of the system. So you may, if this is very small, you will move around the eigenvalue of the system. And since the adjoint is the way you will project the dynamics onto this unstable direction, you will modify the eigenvalue with this quantity. So you have to evaluate the modification of the operator with the direct and the adjoint global mode, and this is rescaled by the scalar product between the direct and the adjoint. So if the two are making nearly a right angle between each other, this coefficient will be very small, so the modification of the eigenmode may be very large. So there is two messages here. First, the adjoint eigenmode is the way to project the dynamic onto a particular eigen direction of the system. And now you have two different behavior, transient growth or sensitivity of the spectrum of the system. So now what is specific when you do Navier-Stokes equation? So when you do Navier-Stokes equation, you linearize around the base state. So the transport operator will give you two terms, the transport of the base flow by the perturbation and the transport of the perturbation by the base flow. Very easy. So now you compute the adjoint. I do not justify why this is the adjoint, but when you compute the adjoint, you will transpose this matrix, and you will change the sign of the transport term, like that. So this is well known. The fact that you transpose this matrix will give rise to the lift-up non-normality, and I will explain in the next view graph what I meant by that. And this other term, now that will change sign, I will show you that this is what I will call the convective non-normality. This will have also an impact on the non-normality of the system. And I propose a new name, since my chairman is from Japan. I propose the convective modoki, because modoki is, maybe you correct if I'm wrong, but this is a Japanese name that means something that is similar but yet totally different. So only Japanese may have this type of very nice concept. And this is a convective modoki because this will have the flavor of the convective instability, but this is not the convective instability. This is due to the non-normality of the system. So, so what are these two physical mechanisms? First, the lift-up mechanism. You all know that if this is a flat plate, you have a shear, a boundary layer on the flat plate. So you have a shear. As soon as you move normal to the shear, some particle, you will create a very large traffic jam in the flow. So you will create with a small v, because you transport along the gradient of the base flow. So this is transport of the base flow by the perturbation. You will create very large u. So if you take the adjoint equation, it will be the reverse. You need very small u to create very large v. So with the lift-up non-normality, the flow is highly non-normal because all the response of the flow is on u, and all the sensitivity of the flow is on v. So if you look at eigenmode, all the eigenmode will be on the direction u, on the component u of the vector, and all the adjoint mode will be dominated by the cross-stream component, on component v. So this is a non-normality due to the component. Direct and adjoint global mode are, I'm dangerous with a laser pointer, but even with that. The two are orthogonal between each other because they are on different components. So this is a component-driven non-normality. So now what is specific with the transport term, so the other term when you linearize Navier-Stokes equation, is that it will change sign between the direct and the adjoint. And this is a very simple idea. If you do something in a flow and there is a mean transport, the response of the flow will be downstream, and what you should do, so the sensitivity of the flow will be upstream. So this is this very simple idea cast into this non-normality things. So this is an example due to Gianetti and Lucchini. He did that for the wake of a cylinder. So the energy, so this is the energy of the direct eigenmode. The energy of the direct eigenmode is downstream. The energy of the adjoint eigenmode is upstream. And now you have also a non-normal behavior, because the direct and the adjoint mode, they will be orthogonal to each other because they are localized in a different part of the space. So they are not they're localized at the same location. So it's a different way to be non-normal and to have transient growth. So now let's apply that to the case I was dealing with at the beginning. So the flow in a duct with recirculation bubble. We do standard technique to compute the steady state. We use FreeFM++, that is a nice French software, free software to compute equation. We use RPAC or UMFPAC to compute the global mode. So now if we do the stability of the flow, you will have to look for some particulars. So you will have, this is a duct, infinite duct. So you will have the span-wise wave number Z, and you look for span-wise wave number Z, you have the perturbation that correspond to that, the eigen perturbation. So what we obtain is that we have the flow for the particular configuration we are considering that will bifurcate at Reynolds number 700, and it bifurcates for, so this is the growth rate at the threshold, just above the threshold for the different span-wise wave number. So you see that you destabilize for a wave number that is close to 2. So this is a 3D instability. And this is a stationary instability. The little circle here represents the frequency of the mode. So this is a zero frequency instability. So this is a stationary instability that will break the invariance in the Z direction.
What's lambda 0? Lambda naught?
Lambda naught. Where is lambda naught on the graph? Okay, this is so this is just this is the real and the imaginary part of the. So this is just the growth rate, and this is the frequency. Just maybe a bad notation. You're correct. So what is the shape of the mode that will destabilize the flow? So this is the streamwise velocity that corresponds to the direct global mode. So this is the streamwise velocity. This is a plot. If you integrate for the perturbation, you integrate the total energy of the perturbation. And in little dot, this is the contribution of the streamwise part of the total energy for the global mode. So we see that this global mode is dominated by the streamwise component. And if we add the global mode to the base flow with an arbitrary amplitude at this location, we obtain this type of perturbation for the magnitude of the streamwise vorticity. So this global mode corresponds to the formation of low and high speed streak. So here you have a low speed streak and high speed streak. So this mode is driven, the energy of this mode or the mechanism of this mode is due to the lift-up mechanism. So this mode is involving the lift-up mechanism because all the perturbation energy is on the streamwise component for that. So now, if we compute the adjoint global mode for that, so this is the adjoint global mode also for the streamwise component. This is the total energy of the adjoint global mode. This is the contribution of the cross-stream perturbation. So in the recirculation bubble, the adjoint global mode is on the cross-stream perturbation. But you see that the adjoint global mode, this is not a parallel flow. So the adjoint global mode peaks onto the separation point. This is not a big discovery because we know that this is the most sensitive part of the flow. And if we add the adjoint global mode to the base flow to see what is the effect of this adjoint global mode, the effect, and we zoom on the separation point, the optimal perturbation for this, so the adjoint mode represents the optimal perturbation, and this corresponds to move around the separation point. But the message here is that if we look at the energy of the adjoint global mode, the energy of the adjoint global mode is in the recirculation bubble and upstream. The energy of the direct global mode is in the recirculation bubble and downstream. So the two are split in space, as I was mentioning. So what you can do, and this is an idea maybe that go back to Alexandro papers, also for the modification of base flow, is that now you may say, okay, if I imagine that I modify the base flow or I modify the viscosity, you modify something in the equation, and then you will modify the operator for that. And what you will get, so you will have a sensitivity. You know that we have to evaluate the effect of this modification with the direct and the adjunct global mode. So what we represent the sensitivity to base law modification, you have to use the product of the direct global mode with the adjunct global mode, and this will be something that is localized, because the direct global mode is downstream, the adjunct is upstream. So this is something that will be localized. So if you want to modify, raise the wave maker in the system, if you want to have an impact on this instability, you have to modify something inside this region in the recirculation bubble, where the adjunct and the direct are not zero, and this you will have an impact. If you do something downstream or upstream, you will have no impact on the stability of the flow. So this is an important idea. I still have maybe 4 minutes, I think. Yeah? Okay. I have a clock on that. So we may do, now let's do so this was the global mode. What we may do is to optimize, to compute optimized perturbation. What are at one particular instant, what is the most dangerous perturbation for the flow? So we did that for 2D perturbation and 3D perturbation. This is a view graph for the 2D perturbation. So what you may do, you may try for particular instant to find the initial perturbation that will optimize the gain of energy, and you do that for all the instant. And what we obtain in that is that the most, you will see, it's maybe not the most unstable, but the largest gain, you will obtain a very large gain in this flow, but with 2D perturbation. And if you look at what is the optimal initial perturbation and the development of this initial perturbation, what you do in that flow is that this optimal perturbation, so the transient growth, is due to the Kelvin-Helmholtz instability. So you will have our type of perturbation that will trigger Kelvin-Helmholtz type of development of the flow, and this is the way you will amplify the most the perturbation. So the transient growth in that flow is dominated by the Kelvin-Helmholtz instability. So you may do that for all the wave numbers. So you see that there is a plateau here. There is many wave numbers that have similar growth rate, but this transient growth is all governed by this Kelvin-Helmholtz instability. And the funny thing is that now if you take the Reynolds number, you vary the Reynolds number, the time at which the optimal gain is obtained is nearly stable. So this is 14. And here I will plot the optimal gain I may get. And here I will plot the gain if you the gain you have if you take the unstable global mode and you compute the growth you have after 14 time scale. So you have a transient growth with a characteristic time that is about 14 characteristic time of the flow, but you have also an instability after the threshold Reynolds number, but this instability is very weak. It will give you very low growth of the perturbation. So to compare that, we have plot the exponential of the sigma of the leading eigenmode times 14 the typical time for the transient growth, and you see that there is two different scaling. This one, you have a growth rate that is about a gain in energy that is about 1. So this is an instability, but not very strong. It will not give you large gain. So you will need very long time to dominate the flow. But now, if you look at the transient growth, you will have something that is the larger the Reynolds number, the larger the growth rate of that. So if you imagine that you look at a real experiment, you have a real tube, then what you will get, maybe you will never observe this instability, but you will observe the amplification of perturbation. Maybe just we'll do a final point. So I go through the jokes. So this is joke. This is very funny, but we have no time for that. I just want to say something for the here. This is the important. Let's do that. The important. So what we did is for the wake of a disk. What you may do is that now you may compute the normal form. So you may compute weakly nonlinear theory. When you compute weakly nonlinear theory, you have to project all the dynamics using the adjunct global mode. So you will have some forcing at different order. You have instability that develop in the flow. So this instability will produce a modification of the flow downstream and harmonics that will be downstream. But if you want to compute the nonlinear behavior of the flow, you have to project all this forcing using the adjunct global mode. And when you do that, in the Landau type of equation, if you want, what you will obtain is that you have a forcing term that you may compute in the expansion, and you have to evaluate that with the adjunct of the global mode. And the end result of that is this nonlinear term, forcing nonlinear term is downstream, this is only upstream. So the region where there is a coupling between the mode is localized, and in this particular case is localized in the recirculation bubble. So the message here is that also for the nonlinear interaction, the adjoint global mode will define why the flow is sensitive to perturbation. Thank you very much.
Questions?
The output, is that after T14, is that still the global mode then, or is it not enough time? So I mean, the input of course is not, but
No, so what the other curve, we were just putting in the global mode and looking how much the global mode will be amplified. So the input is the global mode, it's not the adjoint. We may have put the adjoint, but this would have given a gain of order 6, but not a gain of order 10 to the, of order 10 to the 5.
in the case where you have the gain of 10 to the 5,
Yes.
The input is probably close to the adjoint, but what about the output? Is that close to the global mode?
No, not at all, because the input will be more like you have to trigger the Kelvin-Helmholtz instability. So the input is all localized on the separation, but it's like our mechanism. So the picture I've shown. So it's totally different from the adjoint global mode.
If you wait long enough, then it will be the optimal, would be the adjoint.
Yes, but this is
too short then.
But this is not the maximum of the gain, so there is no point to wait that long. This is not what you will see if you put noise on the system.
Can I move on to the second talk?